All the science terms, they're either in English, and if they're not English, it's probably German. Are we rolling? Okie dokie. Hello, everyone. Welcome to Chapter 10, our lesson on volcanoes and other igneous activity. Great word there, igneous. Remember from our lesson on rocks, we've already learned that word igneous means rocks that were formed by the cooling of magma. Remember, magma is our hot liquid rock buried deep in the earth. When that rock cools and becomes solid again, we call it igneous rock. Remember, there were two types of igneous rock. We broke it down into two main categories. We have our extrusive rock. That's lava that cools out. That's cooled lava that has already erupted. And then intrusive. That's when magma cools inside of the earth. So intrusive, inside. Extrusive, when that magma exits, becomes lava and then cools. These two terms we're going to come across several times in today's lesson. With that, let's move on. 10.1. The nature of volcanic eruptions. There are, of course, several factors that determine the violence of an eruption, that is, the force of an eruption. We've got the composition of the magma. Remember, we've learned about, when we looked at rocks, when we looked at rocks and minerals, we talked about composition a great deal. We learned about the presence of high silicate minerals like feldspar and quartz. We see these in like rhyolitic rocks like granite, those rocks with a lot of silicates. At the other end, we have the low rocks that are very low in silicate material, low in the silicates, and higher in the alkali metals and the alkali earth metals. These are going to be our more basaltic rocks. So remember, basaltic is going to be low silicate, high alkali. Our rhyolitic is going to be high silicate, low alkali. We're going to look at both of these terms closer in today's presentation. So if you can't remember these words right now, don't worry. We're going to talk more about it. Another factor, the next one being the temperature. How hot is that magma? Obviously, hotter magma is going to have faster moving molecules. They're going to be farther apart. There's going to be more pressure. And that lava is going to be more liquidy. As it cools, it's going to become solid. It's going to freeze. But hotter magma is going to be melted and liquid. The dissolved gases in the magma. Remember when we learned about how thermal vents can affect the composition of magma, because all of that hot water in the vapor form can be carrying a lot of different dissolved minerals and dissolved gases with it. So a lot of these gases can be dissolved in the magma, and it can really change how violent the eruption is. The next thing we're going to look at, and we're going to talk about this throughout the lesson, is viscosity, our V word, viscosity. This is the measure of a material's resistance to flow. So a material, something that flows very easily, like water, is going to be called low viscosity. Something that flows very easily like water, or like a paint thinner, would be very low viscosity. If it's high viscosity, there we're talking about things that flow very slowly because they're very thick, like syrup or paint. So remember, low viscosity, they're very thin, like water. They flow quickly and easily. High viscosity, they're very thick, like paint or syrup, and they flow slowly. So low viscosity, thin, flows quickly. High viscosity, thick, flows slowly. Let's look at some factors that affect eruptions. Here we're on page 4. Another one, we talked already about dissolved gases. Mainly, when we talk about these gases, that's water vapor, which we already talked about, and carbon dioxide. Of course, these gases will expand near the surface. That's because as the lava and the gases come up towards the surface, there's going to be much less pressure on those gases. Remember when we talked about sedimentary rock? We said that that rock forms because the different layers keep coming down on top of the rock, and they push down to create a lot of pressure due to gravity. So at the bottom, there's going to be a lot more pressure. You can think about this. Imagine a human pyramid. Imagine if you're making a human pyramid like you do on sports day. Someone at the bottom of the pyramid is going to have to carry a lot more weight than someone at the top. It's the same basic principle that applies to fluids and applies to rocks. When we're deep down, we're under all that gravitational pressure. So the gas is under a great deal of pressure. As it rises, the pressure is much less, so the gas is free to expand. So gases are going to expand near the surface. The next point, a vent is an opening in the surface. We use the same word for vents in a window or your house or in your car. Any opening where air can come through, that would be a vent. And we use that same word in geology. A vent is an opening in the surface of the earth that gas and liquid rock can rise up through that opening. And all that expansion and all of that pressure, that's what creates the force to push out that lava, that magma, to push it up, to erupt to the surface, become lava, and then cool into that extrusive igneous rock. More about those dissolved gases. We know the violence of an eruption is related to how easily the gases can escape. So if the magma is very fluid, that is very low viscosity, very thin, low viscosity, the gas can escape easily. But that very high viscosity, thick lava, the gas has a hard time escaping. You can think about it this way. If you ever make a gelatin or a jello mold, sometimes after it cools, after you're finished, you can see bubbles of air in that jello. But if you have just a glass of water sitting on a table, you're not going to see those same bubbles. That's because the water is very low viscosity, so any air in the water can escape easily. But that jello, that gelatin, is very thick. It's very high viscosity, so the air becomes trapped. The air cannot escape. it's the same. Try to imagine how easy it is to stir your finger in water versus stirring your finger in Jello. It's very difficult to push your finger through Jello. So the same thing applies to the air. The air bubbles cannot push their way out. So that highly viscous magma, that thick magma, is going to have more air. And so that all that air, that gas, is going to expand very quickly when it gets to the surface. So that thick, viscous magma is going to create a more violent eruption. It's not just very low viscosity magma might just run out of a mountain and run down the sides. But the high viscosity, thick magma is going to explode from a volcano. All right. On slide 6, we see some of the factors that affect the viscosity of that magma. And I want you to let's look at the left side of that table. Notice on the top we have that basaltic rock. Notice there our silica content is the least. It's less than 50% silica. Remember, our silicates were like quartz, which is just silicon dioxide. And another silicate was feldspar. Those are the two most common minerals in the world, and they are both silicates. But the basaltic rock is going to have the least amount of silicate. It's going to have more of those alkali metals like sodium and the alkali earth metals like magnesium and calcium. So the alkali metals, sodium and potassium, are alkali earth metals, calcium, magnesium and calcium, and more of the transition metals like iron, cobalt, nickel, and aluminum. And those are going to be our very low viscosity. The low viscosity lavas, the low viscosity magmas. So those are going to be the very thin, runny magmas. Notice down at the bottom, the rhyolitic. They have the most silicates. Remember, so that's our feldspar and our quartz, like our silicon dioxide. They have more silicates and less of the alkali metals, the alkali earth metals, and the transition metals. And those are going to be the very high viscosity lavas. The high viscosity magmas that trap more air, more of the water vapor, more of the carbon dioxide, and they're going to have the more violent eruptions as a result. So, yeah, basaltic, less silica, lower viscosity. It's going to be more runny, more liquid, more like a liquid, more thin. The rhyolitic, more silicates, higher viscosity, very thick. So more syrupy. Here we go. On slide 7, look at our lava flows. Basaltic lavas are more fluid. Right, they're more low viscosity. Those basaltic lavas with lower silicate content, they're lower silicates, lower viscosity, more fluid. So the eruption is not as violent. That gives us Pahoho lava, which looks like the braids and ropes, and lava, like rough, jagged blocks. We're going to look at pictures of both of these, Pahoho and lava. Both of these are Hawaiian words, by the way. And then also the other important volcanic material, gases. They are about 1 to 5% magma by weight. A lot of famous pictures of volcanoes when we see like Mount St. Helens or Mount Pinatubo in the Philippines. Those pictures, you see the large columns of gray smoke coming up from the volcano. That's that gas that's mostly water vapor and carbon dioxide, and about 5% of that is magma. Here you see the Pahoho, the ropey lava, glowing there, flowing down the mountain. And there, that slow-moving lava. You can see there are two geologists. They're on slide 9, either very brave or very stupid. Maybe a combination, but they're walking in front of a lava flow. And they're able to do that because that lava is moving very slowly. That lava is... and so remember, it's moving very slowly because it's very high viscosity lava. And remember what we learned about that high viscosity lava. The high viscosity lava is going to have the high silicate content. So that lava, the slow-moving lava, high viscosity, high silicate content, and not much of the alkalis. That Pahoho, the ropey lava, it's lower viscosity, lower silicate, more of your alkalis and your transition metals in that. And that's going to move much faster. It's also that Pahoho is going to be the type that has lower amount of gas like water vapor or carbon dioxide. The lava, the thick, high viscosity lava, is going to have more water and carbon dioxide. You can see in that picture of the lava, you can see the little what look like clouds of gray coming off of that lava. That's the steam, that's vapor. That's because that lava is high viscosity, it's thicker, it has trapped more of that carbon dioxide and more water vapor. So it's going to create more steam when it starts to flow. Yeah, so just remember, high viscosity means high silicate, means higher level of carbon dioxide and water, means it moves slower, and it's more violent. All right, next. Pyroclastic materials. These are the materials, these are the name given to the particles produced in volcanic eruption. The little pieces that come out of a volcano. The fragments ejected during eruptions range in size from a very fine dust to pieces weighing several tons. I talked just a moment ago about Mount Pinatubo in the Philippines, or Mount St. Helens in the United States. When you see the big column of gray smoke going up into the air, that's because we have very, very small particles of volcanic ash. Particles that are less than 2 meters across. And that ranges all the way to pieces weighing several tons, giant pieces. I know a few years ago I climbed Mount Fuji, which is a volcano. And there, the whole mountain is covered with particles about this size. So it's like the whole mountain is made of gravel, small stones. All of the pyroclastic material at Fuji is little stones. On the next slide, 11, pyroclastic material, we have different categories. We've got the ash and the dust, the very fine fragments like we see at Mount Pinatubo. Next, pumice, frothy air-filled lava. Pumice is very interesting because there's so much air trapped in that lava that when it hardens into pumice stone, it's still full of air bubbles. So remember, pumice would come from very high viscosity, high silicate lava. So if you see pumice, you would know there's a lot more silicate than the transition metals or the alkali metals. But what's interesting about pumice is there is so much air in pumice that it will actually float on water. So it's a stone that is lighter than water. So rather interesting to see that. Then lapilli, which are walnut-sized particles, and you see a lot of that at Mount Fuji. Then cinders, which are very small pea-sized particles. But yeah, the lapilli is what I saw when I climbed Mount Fuji. A lot of particles about this big. And all of them the same, like red-brown color. And they're supposed to be very bad luck if you take one home. Then if we go bigger than lapilli, we have blocks of hardened lava, and then the bombs, which are the word for hot liquid lava that's ejected. And obviously, bombs would come from a more violent volcano. So volcano that had a lot of gas trapped in the magma. So more high viscosity, high silicate magma. Types of volcanoes on page 12. There are three main volcanic types. That is a shield volcano, a cinder volcano, and a composite volcano. And the type of volcano has a lot to do with the type of lava. We're going to talk a little bit about that right now. We're going to look at a picture of that in a couple slides. But first, what do we know about a volcano? The basic term. A volcano, it is a mountain that is formed of lava or pyroclastic material. So I talked about Mount Fuji, all those lapilli, the pyroclastic material. That would be, Mount Fuji is a volcano. Then the crater is that depression at the summit, which is produced by meteor or that which is produced by meteorite impact. We use that word crater either to describe the top of a volcano or what happens from a meteorite. Don't worry about the meteorites right now. That's a completely different lesson. Then we've got that conduit or pipe which carries the gas-rich magma to the surface. You can see all of that on the next page, 13. You've got that mountain of pyroclastic material. Then that conduit is that purple vein moving up the top. That's almost like a pipe, an open area. And then we have that vent and the crater at the top. Okay, so different types of volcanoes. We already said that we have three different basic types. We've got the shield volcanoes, the cinder volcanoes, and the composite. We're going to look at those right now, and we've got a few pictures as well to help you understand. Shield. Those are very broad, gently sloping volcanoes. They're built from very fluid, balsatic lavas. So remember, they're highly balsatic, they're very fluid, they're very low viscosity, low silicate, low viscosity. They're going to have more of the alkalis and the transition metals. So they're not going to explode. They're not going to build these big steep cones. Lava's going to flow out of the earth slowly and give this broad sloping volcano. That's a shield volcano. You can see that on slide 15. There's an example of that. A good example would be some of the volcanoes in Hawaii. You see there's one of the Hawaiian volcanoes that would be an example of a field volcano. But we're going to look at both in the example of Hawaii. Hawaii is very interesting. The next type, cinder. A cinder, back on slide 14, cinder cones are small volcanoes built primarily of pyroclastic material ejected from a single vent. They're going to have a steep slope, they're going to be smaller, and they usually occur in groups. There's a good example of that on slide 16. You can see there's a cinder volcano, and we've got a group of cinder volcanoes there. The one on the left appears to be much newer, like it recently erupted, and its brothers and sisters there to the right are probably much older, because as you can see they've kind of eroded, and so they're much more round on top. But yeah, these cinder cones, they occur in groups. So not so much basaltic. Here we're moving into the more andesitic or rhyolitic lava that has more silicate and higher viscosity. Higher viscosity, higher silicate in the cinder cones. Next is our composite cones. These are volcanoes composed of both lava flows and pyroclastic material. Many of them are adjacent to the Pacific Ocean. Yeah, we talked in the last lesson, chapter 9, about the ring of fire, that ring around the Pacific Ocean where the Pacific plate is shifting around and forming different types of boundaries, different types of fault lines. Like in California, the west coast of the United States, you have a transverse fault. A transverse fault zone. Then you have in the Andes, you have more of a convergent zone there. Let's see, most are adjacent to the Pacific Ocean, okay, like Mount Rainier. These are going to be much larger volcanoes. Remember, our cinder cones were very small. Our composite cones are going to be much larger, and they tend to be the most violent. There's an example of a composite cone on slide 18. Here, excellent. On slide 19, we see Mount St. Helens before and after the eruption. Notice before the eruption, it's got this beautiful even slope, almost like Mount Fuji. But then after the eruption, the whole side is broken down, and yeah, and so there's ash and cinders everywhere. All right, okay, here we go. Profiles of volcanic landforms. Perfect. You can see the three different examples here, and you can see the very, very different shapes. That one up at the top, Mauna Loa in Hawaii, which is a large shield volcano. The first type we talked about, remember, the very low viscosity, low silicate, high in alkali metals and transition metals. So there's not much gas trapped in the lava, so the eruption is not very violent, so the lava just flows out very evenly and forms this flat dome. That's Mauna Loa, an example of a shield volcano. Notice down at the bottom we see Mount Rainier and Sunset Crater in Arizona. Sunset Crater in Arizona, that's our cinder cone. As you can see, they are much, much smaller than the other two. And then Mount Rainier, a composite cone. They're going to have much more violent eruptions because of the high silicate, high viscosity lava that has a lot of gas trapped in it. So there's going to be much more pressure, so the eruptions are much more violent. Other forms, caldera. Calderas are very large depressions. They're usually circular, and they are formed by collapse. Sometimes they can be 1 kilometer in diameter. So they look like almost like a meteor crater. Then lava plateaus, that's that very fluid, highly balsatic lava like you get with a shield volcano. The lava that's very fluid, so very low viscosity. Low viscosity, low silicate, like in a shield volcano, like at Mauna Kea in Hawaii. They form these flat plateaus. So fluid, balsatic lava extruded from crustal fractures called fissures. The next, plutons. We're going to talk about plutons for the next several slides here. There are many different types of plutons. Plutons are intrusive igneous structures. Remember from our unit on rocks, when we talked about igneous rocks for the first time, we learned that we broke our igneous rocks down into intrusive and extrusive. Remember, our intrusive igneous rocks are the rocks that form when that hot liquid magma cools and freezes and hardens into rock inside the earth. That's intrusive. Remember, when the lava erupts and it cools and freezes and hardens outside on the surface of the earth, that's called extrusive. Here with plutons, we're talking about rock formations from intrusive lava. So before we go on to the next slide, I want you to just think for a moment. If these plutons are intrusive and they form beneath the surface of the earth, if they form underneath the earth, how is it that we see them? What has to happen first? Well, remember, we talked about how earth and soil can be carried away when we talked about the formation of sedimentary rocks through that process of erosion. So yeah, for us to see these intrusive structures, first they have to form inside the earth, and then the earth is washed away. Remember, we've talked about this in several of our previous lessons on geology. Let's move on. Let's talk about different types of plutons. First, sills and laccoliths. They are plutons that form when magma is intruded very close to the surface. So there's not much earth on top of them, so the earth erodes away very quickly, and they are exposed very quickly. Sills resemble buried lava flows and may exhibit columnar joints. Laccoliths are lens-shaped masses that arch overlying strata upward. Here on page 25, we see an example of a sill. You can see there that sill was formed, and originally it was intrusive rock, meaning that it was buried at first, but after years and years of erosion, those sills have become exposed, and they form those columns. One type of rock that forms this a lot is basalt. Boom, boom. There we go. Basalt very often forms sills like this. Let's move on. Next are dikes. Dikes are tabular-shaped intrusive igneous features that cut across pre-existing layers. They form when magma from a large chamber invades fractures in surrounding rocks. So if you've got a crack in a rock. It's all older rock that's there, and the lava fills in that crack. That's what we call a dike. And I think you can see a few examples of that on slide 29. If you look especially in that picture on the left on slide 29, you've got the dikes are those things sticking up to the spike, like spikes to this in all directions from the batholith. So there were cracks in that old rock, that old sedimentary rock, and the hot liquid magma filled those cracks to form the dikes. But moving back to slide 27, the other type of pluton we're going to talk about, batholiths. That's that large mass of igneous rock. We've already learned about batholiths as the basic form of intrusive igneous rock, like when magma cools inside of a magma chamber. You can see a picture of an exposed batholith on slide 28. That's a batholith that's been exposed for a long time and has been eroded. You can see a good, and back to that picture on slide 29, you can see the batholith deep underneath the ground and the dikes branching off of the batholith. And then, this picture is excellent because you can see the sills as well. The sills are those lines of dark gray magma that fill in areas between the different layers of sedimentary rock. So you can imagine with a sill, we have a layer of sedimentary rock and then lava coming and filling in an area, laying down a layer of magma, and then more sedimentary rock forming on top of it. That forms that formation like in slide 25, where we've got that layer of igneous rock. Okay, let's move on. Slide 30. About the origins of magma. Geologists conclude that magma originates. Originate means to start or to begin. So magma starts when solid rock melts. When we looked at the rock cycle, we saw how this happens, how the rock in a tectonic plate is pushed down in a subduction zone. The rock is pushed down deep into the earth, into the asthenosphere, where it becomes very hot, it melts, it turns into magma. The most obvious way to generate magma from solid rock is to raise the temperature. So at very high temperatures deep in the earth, the rock melts, becomes magma. Next, slide 31, the role of heat, the geothermal gradient, which is Earth's natural temperature increases with depth but is not sufficient to melt rock. We can't do that in the lower crust and the upper mantle, so we need to get additional heat from friction. Remember when we talked about subduction zones? We've got those two tectonic plates rubbing against one another. You know, if you rub your hands together, they'll start to feel hot from friction. The same thing applies to two tectonic plates. If they're rubbing together, there's going to be a lot of friction and therefore a lot of heat, and that heat energy can actually melt the rock. Crustal rocks heating during subduction, then we get that hot mantle rock. All right. Next, on intrusive igneous activity, we've got the role of water on slide 32. If there is water in the rock, water will actually cause rock to melt at a lower temperature. And this plays an important role in those subducting ocean plates, because underneath the ocean, obviously there's going to be more water slipping into those cracks in the subduction zone. So in the underwater subduction zones, the melting point of that rock is going to be lower, so it's going to melt faster, and so you're going to get more liquid magma in a subduction zone that's under the ocean. Page 33, we see an example of basaltic magma at the surface. Remember, basaltic magma is our very low silicate, high alkali lava. So because of it's low in silicates, it's going to be very low viscosity. It's going to be more liquid. So you can see that hot liquid magma there. It almost looks like water splashing around. That's because it's low in silicates. You can go back, compare that to the lava that we saw back on slide, whoopsie-daisy, back on slide 9. See how different that is to that slow-moving, very solid lava that's lower in silicates and higher in our transition metals. Yeah, so low viscosity, low in silicates. Okay, where are we? There we go. We're at basaltic magma. Next, our convergent plate boundaries. We learned about this in our lesson on plate tectonics. This is where two plates are coming together, like where the Indian plate is smashing into the Asian plate, where pushing up the Himalayan mountains, where the Pacific plate is pushing into the South American plate to form the Andes Mountains. The basic connection between plate tectonics and volcanism is that plate motions provide the mechanisms by which mantle rocks melt and generate magma. Okay. Ocean, rising magma can form volcanic islands. A good example of this is the Aleutian Islands. Whoop, damn it all. We talked about the Aleutian Islands yesterday. This is a convergent plate boundary. There are two ocean plates coming together and pushing up the Aleutian Islands. Again, the Andes Mountains in South America, which we talked about yesterday. That's an example of an ocean plate meeting a continental plate. So we've got that rising magma. Next, slide 35, you see a great example of a convergent boundary volcano. Notice there we've got a lot of ash going into the atmosphere in that volcano. So that's going to be a very high intensity explosion. So that's going to be very high viscosity, high silicate lava. All right. Divergent plate boundaries on page 36. The greatest volume of volcanic rock is produced along the ocean ridge system. This makes sense. Where is the most lava going to come to the surface? It's going to come in the places where the plates are being pulled apart. So where the plates are opening up, that's where the lava is going to have an open door to rush to the surface. Remember that we saw that in the Mid-Atlantic range, a divergent plate boundary. We saw that in Africa's Rift Valley, another divergent boundary. That's where the most lava is coming up to the surface. That's where we get the largest quantity of basaltic magma. 37, intraplate igneous activity. This means igneous activity within a tectonic plate away from any plate boundaries. We saw this yesterday with the Hawaiian Islands. Remember, the Pacific plate is actually twisting and it's moving over that weak spot where the magma is coming up, and that's what's forming the Hawaiian Islands. It's not a boundary, it's just a weak spot in the plate, almost like a hole in the plate where the lava can just shoot right up. Examples include the Hawaiian Islands and the Columbia Plateau. And on the last slide there, 38, we see Kilauea, which is an intraplate volcano in Hawaii. Again, notice that lava looks very liquid, so it's very low viscosity, so very low in silicates, so very more of the alkali metals, so that's what we would call our balsatic lava. So that's going to form more of a dome like this, and not those round shield volcanoes. All right. So that a little bit about volcanoes. Thank you all for tuning in, and I will see you in our next chapter. Thank you.